Assalamu alaikum, dear students. In the previous video lesson, we were talking about wave interference. We started with superposition. We said it is the overlapping of two or more waves. And then after that, the superposition principle, like in simple words, we said if two waves are on the same side, we combine them. If they're on opposite side, we subtract them to find the total. And then we also said that once we combine them and subtract them, that lead to something else, which we call it interference, all right? We said there are two main types of interference. One of them, it is called constructive interference. The other one is called destructive interference. But the destructive, it becomes two types, completely destructive and weakening destructive. We said for constructive, the two waves must be on the same side of equilibrium here. So both positive, both up, or both down. So we add them, so we get a larger resultant amplitude or wave, we can say. But for the destructive, it is either complete, where the two waves are on opposite side and they have equal amplitude, so these two cancel out, so the resultant becomes zero, or becomes weakening, the resultant becomes less, but it's not exactly 100, exactly zero. Where does the 100 come from? I have no idea. All right, then the next thing we were talking about was the type of reflection one. We said we have two types of reflection. There is a free boundary and there is a fixed boundary. We said for free boundary, the waves are reflected but not inverted. But for fixed boundary, the waves are reflected and also inverted too. As a result of free boundary, there's always constructive, and then destructive would be the result of a fixed boundary. And these are what we've studied. And then we ended up right at this point here. And then today we'll talk about standing waves, okay? So what is standing wave and what does it come from, or how do we produce or get standing wave? That is what we're going to talk about. But before we do that, I have something to show you before I forget, and that is we've learned about types of reflection and all that. We also talked about types of, let's say, types of waves and all that. But of course, it's always best to see an animation so that you can see how it works. These are the two types of waves. We have transverse waves and longitudinal wave. Now, for transverse wave, this is how it looked like, and that would be the longitudinal. We also said that the particles in transverse wave, they vibrate up, or you can see that they vibrate at right angle to the direction of wave travel. So if you can see here, for example, if you examine the motion of a particle here, let's say this particle, okay, you can see that it is moving up and down, which is at right angle to the direction of wave travel while the wave is traveling like this. But once again, these particles are moving both up and down while the wave is going this way. That is the motion of a particle in transverse wave. And you can see that here as well. We have a straight line. You can see this particle is moving down and up while the wave is going that way. Now, on the other hand, we have longitudinal wave. And then we said for longitudinal wave, especially if it is sound, there will be regions of where the air particles are closer together. We call these regions compression, and then other regions where there are less air particle, we call them rarefaction. And then this could be the same as the motion of a spring as well. And this red line here could represent the motion of a particle where it can only vibrate or move back and forth, which is parallel to the direction of wave motion. And of course, you can also notice one of this one here. If you look at this, for example, particle here, right, this particle can only vibrate back and forth, which is parallel to the direction of wave travel. And we said we can also represent this as a sine wave too, don't forget. But if it is a sine wave, here must be written pressure or density. Here, this is another word actually. It's written particle compression. We don't have this actually, but it's totally fine, because as long as we have a compression, that belongs to a sound wave. Again, it is either written pressure or density, but this is how it looks like there. All right, so this is one of them. All right, another thing that I need you to see. All right, let's get rid of this one here. Maybe it doesn't work this way. Oh, here. All right. So now that is one. And then the other thing that we talked about, it was the type of reflection. So you can see here, now we have the motion of this. You can see here a pulse on a wave here, but there are two types, or the two types of reflection you see here. One of them, as you can see, that it is fixed end, so you can see that is attached in here. The other one is a free end. So if you examine, this is a pulse that is going. So let's say this is the the line for the wave in here. So this pulse is going, you can see that because the end is free. So when this pulse, it is reflected here and inverted. This would be the pulse that is going, which is above the equilibrium. Once it reaches the end, then this pulse, it just gets reflected and inverted at the same time. But if it is free end in here, you can see that if we consider this is the equilibrium position, this wave, it is just going here, for example. This is the one that is going, but this end has maximum freedom to move, right? So now we can see that this pulse, it is going back, all right, on the same side of the equilibrium here. So this is another thing, the difference between free boundary and fixed boundary too. All right, this is going to be something that, of course, this is the superposition of waves you can see here. When these two waves are moving in opposite direction, in some regions you can also see that here. It is a way slower. Once these two, for example, are crescent trough, that would be 0. But once these two are overlapping, then becomes maximum displacement here. It seems it would have been best if we could pause this one, right? So take a look, for example, at a point here, right? Now watch this one. Once these two are, for example, there, we get maximum displacement. And when these two are both up, for example, this and this one now, we get maximum displacement up. So this will be the superposition, or represents superposition principle as well. And these are what I wanted to show you. There are, of course, more. Okay, but that'll be for the next concept that we're going to study. Okay, so now we can begin with our new concept, and that is standing waves here. What are exactly standing waves here? Why do we call them standing waves? So let me tell you something before we start explaining this one. Perhaps it might help you understand this better. We were talking about, right? We were talking about the types of reflection, right? So the one that is free, and then the one that is fixed as well. So, okay, let's just consider the one that is fixed in here. So this is a fixed boundary here. Don't forget. What happens, we said, if we send a pulse, this pulse is going all the way here. And then after it reaches the boundary, it is going to be reflected and inverted as well. But what happened, of course, we're going to send more and more pulses here. What happened when these two pulses, for example, meet at a point here? Imagine instead of sending a pulse, you can send one complete wavelength in here. Okay, so this would be one. It could be even more than one, actually. Let's just draw this one here. This is when you send a pulse, right? A wave actually into the fixed boundary here. And then this is going to be, let's say this is going to be the reflected wave in here. All right, let's just make this one a bit smaller perhaps. And these two, by the way, all right, these two are supposed to be, by the way, same amplitude. So what happens exactly when these two waves, this is the one that is going here, forward, Masha, and this one is reflected wave here. You can see that these are upside down here. It is exactly opposite to this one here. So now we know that when these waves are, or if there is a continuous wave here, these two waves are going in opposite direction here. So now at some point here, watch this, what happened at this point here. I need you to be careful here. So at some point here, you can see that this is how they're going to interfere. At this point, these are in opposite direction here. So at this point right here, they're going to produce what? They're going to produce a destructive interference in here. But at any point, at any other points, these are going to, like interfere with one another. So what do you think will happen at a certain other times in here? Now these two waves at this point right here, okay, and this one too here, if you draw the diagram correctly, of course, you'll see that these two are also, like for example, on the same side. So at these two regions now, we get a constructive interference here. But these waves are continuing to go in here. So let's just continue at this point here. Let's erase this one so that, right? Now, we said these waves are continuing to move, like at some other point here, that becomes destructive again. So as these waves are moving past one another, there will be regions, constant regions of constructive and destructive interference. As a result of this, we get standing waves here. So this is what it looks like as a result of this one here. We get a wave, all right? So these are by the way, these waves, both ends, we have a string, we can say. Okay, so we will send many pulses here. These pulses are going, and then pulses are reflected and inverted once they reach these boundaries here. So as a result of this, of course, we get something called standing wave there. So this is one of the waves that we can have. What happens once, for example, if we increase the frequency, right? If we increase the frequency of these waves in here, this is how it looks like. So this would be one of them, and then after some time, this wave it is going to be reflected as well. So this is going to be the shape of a wave once it is moving there, because these are constantly moving. Remember, the particles have maximum freedom to go up and down here. So this would be what happened here. So when a shape or when a wave looks like this, that is what is called standing wave. All right, now let me tell you now what is exactly a standing wave. So we'll say standing wave, it is a wave pattern. It is the shape of a wave when it looks like this, Basha. That is standing wave. But when will it form? It will form, Babylon, or it will occur when we have two waves, remember, of the same wavelength, of the same frequency, and the same amplitude. They are moving in the same medium, but in opposite direction, just like what we had, for example, mentioned earlier. Then we can have, or we can get a standing wave. I'll repeat the definition again. Standing wave, it is a wave pattern, Basha, that will be generated, that will occur when we have two waves. Don't forget, two waves of what? Two waves of the same frequency, wavelength, and amplitude. Okay, so it happens when we have two waves of the same amplitude, wavelength, and frequency, and of course these are moving in opposite direction, right, in the same medium. Once these two waves interfere, as a result of this, we get standing waves here. So these are standing waves. Now let's analyze standing waves a little bit more. And the reason why we call them standing waves is because unlike the other waves, they're not continuing, for example, to move from one place to another. They're almost something like trapped between these two fixed points here, so they can go back and forth. Instead of transferring energy, they store energy instead. So this is why we call them standing wave here. Okay, so another reason, so now once we have a standing wave, this is, let's say, a standing wave that we can have with a minimum frequency. Basha, so this is going to be the result of a standing wave right here. Okay, but after some time, of course, this standing wave, right, can switch side and go, for example, to the other side in here. Now, there are regions on this standing wave. Don't forget, at the end of every, or the ends of every standing wave here, right, these are the ends that are fixed. These are called, these we call them, or these parts here, we call them nodes, Basha. So this is a node, and this side is also a node, Basha. So we will just use the letter N for nodes in here. So what exactly happens at nodes? You can see that the particles are restricted, so there's zero displacement. In other words, we can say at nodes, there is no vibration at all, Basha, zero displacement. But at this point here, all right, you can see that the maximum displacement from the rest position here, we don't call it amplitude any longer. By the way, we call this point here, we call this point right here, we call it antinode, Basha. What do we call it? Antinode. Or antinode, doesn't matter. Antinode. At antinode, the particles have maximum freedom of, let's say, to vibrate, or maximum freedom for the particles, because now they can vibrate. Basha, this is what is called a standing wave. Once again, where does this come from? This comes from two waves moving, Basha, two waves of the same wavelength, of the same frequency and the same amplitude, but these two waves are moving what? In opposite direction, and then they meet at the same medium. Then as a result of this, we get standing waves in here. Basha, this is one of the standing wave that we have, Basha. So what happens as the frequency increases, of course, or the pulse increases, we can see that, so we get another standing wave here. So this is going to be another standing wave here. All right, so after this standing wave, of course, because it is the particles of the medium are going to displace or vibrate, so at some time here these waves are going to switch side, and this is how it looks like. Once again, so what is the these are, like we said, we call them nodes and antinodes. So again, this is a node, this is an antinode in here, again this is another node, Basha. This is an antinode again. So let's just color them different here. This is another node too. Okay, so if you notice here, right, here we have two nodes and one antinode. Here there are three nodes and two antinodes here. Can I say on a standing wave the number of, here, of course, the number of nodes are more than the number of antinodes. But how much more? Just one more. Basha, that is one thing you need to know. And here we can have, as you can see, three nodes, two antinodes there. Okay, Basha, more information regarding nodes or this standing wave here. All right, now watch this. But if I ever ask you, for example, let's say, Basha, these are vibrations, of course. Can we find the length? These are waves, right? Basha, if it is a wave, of course, now that means we can have the speed of a wave, we can have the wavelength of a wave, and the frequency of this wave too, okay? But the frequency is going to be for chapter 4 here, even though I can give you an idea regarding this one. But what will be the wavelength in here? Let's say the length of course, these waves are on a string, right? So if the length of a string, we can call it just L, all right? So what will be the wavelength of this wave right here that you see? Let's say the length of this string is 10 centimeter, Basha. So what is the length of this wave on the string here? Now, before you decide, you need to know how much of a wave is presented here. Now, let's say this is one full wavelength, right? Okay, how much of a wave here shown compared to this one here? So this is one full wavelength. Can I say this is how much it is shown here? Yes. Isn't that half a wavelength here? Yes. So can I say the length of this string here, right, it is equal to, let's just erase this one, we don't need this any longer. At this point right here, can I say the length of this string, Basha, it is equal to what? It is equal to half of a wavelength here. So whatever the length, which is 10, it is equal to half of the wavelength, which is on this wave here. Basha, what about one full wavelength equal to? Equal to what? You can just cross multiply, so it is equal to 2 times the length. So if the length is 10, 2 times 10, it is going to be 20 centimeter. That'll be the wavelength on this string here. What about the wavelength on the next, for example, on the second diagram here? So assuming that this is, or the length again, the length of this string, it is 10 centimeter, Basha. How much of a wave is this? Now, remember this, once you're looking at this, you always have to look at one line here, right? And by the way, you can, for example, consider from this point to this point. And one more thing, we no longer call these points crest or trough anymore. These are nodes, right? Antinodes, that's it. So no longer, we're no longer using crest and trough at this point here. All right, now regarding this wave here, now you can use the same procedure that I used there. So if you consider, for example, this one wavelength here, how much of a wave is presented here? Again, if this is one full wavelength, isn't that one full wavelength? Yes. So can I say the length of this string here, it is equal to one wavelength? So if the length is 10, that means the wavelength of, on this standing wave, or of this standing wave, it is 10 centimeter. And you can convert that to meter later as well. What happened if we increase the frequency of the vibration as well? So we said lira length dakata, the wavelength, the unbubbling wavelength dakata, length of the string, wavelength dakata 10 centimeter, and you can convert that to meter as well. Basha, what if we increase the frequency even more? In this case, this is what we're going to get. All right, so the more the frequency, you can say, the more these nodes and antinodes are going to become here. So this is the next wave that we will get, Basha. But if the length of the string is again still 10 centimeter, what is the wavelength in here? Now you have to be careful here. So if I consider one wavelength starting from this black one here, isn't that, let's change a different color, man, right? Starting from this point all the way here, isn't that one full wavelength? Basha. So, and then this is also half a wavelength here. So how many wavelengths do I have in here? That'll be one wavelength, all right, and a half. So I can say, what is one wavelength? We can say 1 wavelength and a half, that means 3/2, yes? Or you could just write 1.5, that is totally fine. Of a wave, it is equal to the length of a string here. So we can say wavelength, or 2/3 3 over 2 of a wavelength دكاتة 10 centimeter. And if you want to find the wavelength, then you can cross multiply the wavelength here دكاتة 20 divided by 3. All right, so 20 divided by 3, of course, that is going to be, we can say, how much is this? 20 divided by 3, right? It is going to be 6 point something when you cut out the wavelength. Now it is going to be 6 point something here. Okay, perhaps I need to get a calculator and calculate this one so that you know what it is equal to. No, it is 6 point something, but we'll just do that so that you know what it is. So 20 divided by 3, all right, divided by 3, it is equal to 6.667, and that is, all right, we can say the wavelength here. Now, I wonder if you've noticed this one here. As the oscillation or the vibration here increases, right, have you noticed this, that the wavelength, right, have you noticed that, for example, as these loops or these oscillations up and down increases here, or as the frequency increases, the wavelength of each one of these, or the wavelength of each one of these standing waves decrease? Because the first wavelength, it was 20 centimeter. The second one, it was 10 centimeter. The next one, or the last one here, it is 6.67 centimeter. So as we, for example, increase these, for example, or the vibration, the frequency, the wavelength decreases, Basha, and that is obvious because frequency and wavelength are inversely proportional, right? So up to this point, we came, like so far so good. But hey, now the next point is something very important. If I ask you, out of these 3 diagrams here, in which one of them the wavelength is the longest, or I have maximum wavelength, you would say the first one, Basha. So in Wizari, they'll ask you a question. On a standing wave, like for example, at which case we have maximum wavelength, they will give you a different number of nodes and antinodes. Is it when we have 2 nodes and 1 antinode? Or is it when we have 2 nodes, or let's say 3 nodes and 2 antinodes? Or is it when we have, let's say, I don't know, 3 nodes and 3 antinodes and 4 nodes in here? So you have to make the right choice in this case, but just keep one thing in mind, Basha. When the question says the maximum wavelength, that is always this one here. And then you can write this as a note for yourself. At maximum wavelength, Basha, maximum wavelength, remember this, there are 2 nodes, Basha, and there is 1 antinode here. Basha, that is one of the questions that they might ask you for. This would be the maximum wavelength. They might say, which one of them would be like, what is when the string is vibrating with a minimum frequency? Isn't that the same as maximum wavelength, because these are inversely proportional? Yeah, so even if they say minimum frequency, all right, in that case, of course, there will be 2 nodes and 1 antinode as well. So keep this too in mind. Now, they can also ask about this one here as well. Say, at which one of these cases, or when do we have the length of the string, it is equal to the wavelength here? Didn't we say that here, all right? The length of the string, it is exactly equal to 1 full wavelength. Yes, so we can say the length of a string, it is equal to the wavelength. That is when we have what? When we have 2 antinodes, Basha. Let's just write 2 antinodes. And how many nodes do we have? We have 3 nodes, don't forget, Basha. But man, what are nodes and antinodes? Node is a point on a standing wave where there is no vibration. Basha, if it is no vibration, I also need to tell you this. These nodes and antinodes are the result of constructive and destructive interference. So when we say a node, that is the resultant of a destructive interference. But what destructive? These are complete because that was, or one of the conditions for standing wave, we said these 2 waves must be what? Have the same wavelength, the same frequency and the same amplitude as well. And also they need to move in opposite direction because the amplitudes are the same. So at nodes here, you can see that the resultant amplitude here, it is 0. So that is we can see that will be the result of a destructive interference. What about at antinodes here? That is the result of constructive interference here. Don't forget that as well. There are some notes I'll be telling you shortly regarding this nodes and antinodes too. But just remember, nodes are the result of destructive interference. Antinodes are the result of constructive interference. And these are the number of nodes and antinodes, let's say for the maximum wavelength, and also when the length of the string equals to the length of the wavelength. In that case, of course, there will be 3 nodes and 2 antinodes. So based on what you see, right, if the question is ever asking for nodes and antinodes, remember, right, the number of nodes, it is always 1 more than the number of antinodes in here. So for example, if I have, and we can use this one, of course, to answer questions as well. If the question says, for example, if on a wave, on a standing wave, if the number of antinodes are 2, what is the number of nodes? It is always going to be 3. So if the question is ever asking for the number of nodes, that would be the number of antinodes is always plus 1. But if the question reversed the question, right, says, what is the number of antinode? Okay, we can always say the number of node minus 1. Whichever is given, you can always use this formula to answer the question for whichever the wave is that there is. And now I can show you one thing regarding, perhaps regarding this one. These standing waves there, but maybe something before that. Let's just walk through the definition. If you study tip, maybe after that it will be more useful. So we said standing wave on line kababa, a wave pattern, Basha, that results when we have 2 waves of the same frequency, right? Wavelength and amplitude, right? These 3 must be, all right, must be all equal to one another, and they must travel in opposite direction. Then, of course, we can have a standing wave. These 2 waves interfere, then there will be a standing wave. And then the definition of nodes and antinodes, got my node, it is a point in a standing wave that maintains or keeps 0 displacement. In other words, there is no displacement at nodes. There's no vibration at all due to a destructive, or node is a, we can also say the second part, node is a result of destructive interference. Basha, you can underline this one too. What about an antinode? That would be exactly opposite to this, a point on a standing wave. That is, we can also say that halfway between 2 nodes. If this is a standing wave, right, these are nodes here, a node and a node. Halfway in between, that is, that would be an antinode here, which is right in between the 2 here. Can split into 2. That is halfway between 2 nodes here. All right. So we can say at which the largest displacement occur, and you can also say that due to a constructive interference, Basha, due to a constructive interference. All right, that'll be for that. And here's the diagram. Now, regarding these study tips, these are also important. You need to know. The first thing that we have says standing wave consists of alternating regions of constructive and destructive. So you saw the diagram. In standing waves, we have both regions of constructive, which we call them antinode, and then regions of destructive, which we also call them nodes too. Basha? All right, that's the first thing. The second thing, there is no motion on the string of the nodes here. And whenever there is a node, these are, like the resultant of destructive, so there is no displacement or vibration at nodes here. 3 says standing wave can be produced for any wavelength that allows both ends of the string to be nodes here. There's also this thing I need to tell you. Now, for example, we were talking about the standing wave there, so this is one of the standing wave we can have, Then if the let's say frequency of the vibration increased, you will get something like this, right? So if you increase further, this one can increase even more than this, right? So something like this. So these are all standing waves, and of course it can continue. But can we call this a standing wave, for example? This is something like this, right? So can we call this a standing wave? The answer is no. All right. So there will be, all right, a standing wave as long as both ends of the string here are always nodes here, right? As long as both ends are nodes here, that is considered a standing wave. Wavelength. So whatever the wavelength equal to. And in that case, like it doesn't have, or the wavelength doesn't have to be a full number or whole number or whatever, right? So whatever the wavelength is, it is acceptable as long as both ends of the standing wave where both ends are nodes here. That is the condition. So this is not a standing wave here. Basha? So because if it was here, that would have been correct, but not this one, because both ends must be a node. If it is not a node, then it is not a standing wave here. All right, number 4, we've mentioned that with my minimum number of nodes and antinodes is 2 nodes, right, and 1 antinode. What is the minimum frequency for standing wave? Basha, Gutmanyan, the first diagram you saw here, you can also see this or here again. This is the minimum number of nodes and antinodes for standing wave. That would be this, so 2 nodes and 1 antinode. And then after that, these are more and more, you can say, standing wave here. All right, number 5 says in a standing wave, watch this. The amplitude at an antinode is twice of the amplitude of the individual waves. What do you mean by this? All right, do you remember we said nodes are the result of destructive interference? Yes, Basha. What about the antinode? We said it's the result of constructive interference, right? So imagine this, we have 2 waves, there's a pulse going here, Basha, and then we have another pulse, okay? One of these is moving forward, let's say to the right, OEDK is moving to the left one, yeah? But because these are both on the same side of the equilibrium, right? These are both on the same side of the equilibrium, so what is going to be the resultant amplitude in here? The resultant amplitude, we can say, it is going to be this. Basha, if the amplitude of each one of these, for example, is going to be 2 centimeter, and this is 2 centimeter, these must be the same, by the way. I just draw them a little bit different so that you can see that there are 2 waves, Basha. Let's just draw or go back to this one, so we can only see that there are 2 waves here. If the amplitude of each one of them is 2 meter, 2 centimeter, doesn't matter. The resultant of this the wave here, it is going to be what? This amplitude is going to be 4. Isn't that 4 twice of the amplitude of each one of these waves? Yes, and that is what we mean. So at an antinode, it is the result of a constructive interference, Basha. An antinode, I'll repeat, an antinode, all right? It is the result of constructive. So we have 2 waves, each one of them has an amplitude of 2, and then the other wave has an amplitude of 2. So what is going to be the resultant now? It is going to be 4. And that is the antinode right there. Basha, this is what the last point is mentioning or talking about here. And you need to know that. Okay, but what is the resultant amplitude or displacement at a node? Remember, it is 0 because that is the 2 waves are opposite, so they cancel out completely. All right, so the resultant is going to be 0. All right, so these are some other standing waves. Don't forget, this is where the wavelength, it is equal to 2 times the length. Later, Baba, the wavelength, it is the largest. Later, the wavelength, it is equal to the length of the string here. And then later, the wavelength, it is equal to 2/3, right? This is 3 parts, we can say. So 2 out of 3 parts, all right, equal to, of the length, it is equal to 1 full wavelength. Asha? And this is 1 part, this is 2 part. This 1 full wavelength, which is 2/3 of the length would be 1 wavelength. So try to know when when we have the maximum wavelength sen node antinode here, when the wavelength is equal to the length sen node antinode here, try to remember these because these are Benin Wazari, and of course chances are they will be again. Okay, now a few study tips before going back to the other one. Gutman, the wavelength is equal to twice the length of the string. That would be maximum when there are 2 nodes and 1 antinode. Basha, we can say lambda, it is, or the wavelength, you do know the symbol, 2 times length would be the longest wavelength that we can have for a standing wave. What's the length of the catch? Like B, we just multiply. All right, so the second one here says the wavelength that is equal to the length of the string here when there are 3 nodes and 2 antinodes here, that the length of the string would equal to the wavelength here. And don't forget, we can say every or each loop it is equal to half of a wavelength. That, of course, might make it very easy for you to know how much of a wave is there. So 1 loop, by the way, these these are not circle-like or whatever the shape you call it. This is a loop, like a closed circle. All right, each one of these is considered half a wavelength. Later, it's 1 loop, so half a wavelength. Later, 2 loops, each one of them is half and half. That would be 1 full wavelength here. Here, right? This is half and this is half, so that is going to be one full wavelength here, and this is another loop, so it is going to be here on this length here we have 1.5 wavelength toccata lengthy string decay here. Okay, now regarding the next equation that we have, we'll be going through that, but after this, which is also something very important. So now let's go back to and watch some of these in here. We can say standing wave is the result of constructive and destructive. So you can see that we have two waves, right? These two waves are moving in opposite direction. You can see that these points here, right? These are, you can call them nodes, all right? Where you can see that there is always zero displacement here, all right? Zero displacement. But in between the two, these are antinodes, Basha. Sometimes they go up, right? Once the two waves are up, and sometimes they go down here. But the place of the nodes here will never change because that is the result of destructive interference, Basha. So you can see it's constructive both up and down. This was destructive. You can see that there's a result. These are always maintaining the same zero displacement there. All right, more about this one here. Okay, and that is this one. This might also help a little. Of course, it will help to something else that we're going to solve soon, inshallah. All right, so I need you to take a look at this one here. I'll just perhaps zoom in this one a little. Take a look. These are, again, if we have a fixed boundary, what would be the type of the reflection? As you can see, a pulse is sent, and then the reflected would be on the other side of the equilibrium. So because it is reflected and inverted as well. And now what happens, this is basically going to be the first type of a standing wave here. So the wave, you can see that, right? So this is a node, and in between or the center, it is going to be an antinode, which has a maximum displacement. Right? It is perhaps more obvious once we have the next standing wave too. All right, keep watching. Okay. So you will see now. Oops, sorry. Just go back a little. It's too much. Okay, take a look. Now it is going to point out what are the places. If you notice here, these points, there's almost like there's no displacement at this point, but at the other point here, let's just go back with this one a little, right? Because it was good actually. You can see that at this point here, these are. We need to pause this one again. Okay, at this point here, these are nodes, all right? There is no displacement whatsoever. But at antinodes here, we can see that we can have, or there is maximum displacement. If we consider this is the equilibrium position, the particles can go maximum to the right at some point, and then after that, they're going to be maximum to the left as well. So at antinodes, there's maximum displacement here. By the way, this is going to be the antinode here, right? This will be the equilibrium position, but these are just because the wave is switching, so the antinode is written here. But otherwise, this is how it is going to switch back and forth. But at nodes here, there is no displacement at all at this point here. So you can see there is an antinode up, there is an antinode at this side, or you can say if this is right, this will be to the left. Now they're going to switch sides as well. So this is what you need to know because we have a question that requires this one here. Now what happens once we, for example, increase the frequency, like vibrate this one with a larger frequency, there will be more nodes and antinodes, but the wavelength, in other words, you can say the frequency gets higher, but the wavelength gets shorter. See, you can notice that at nodes, there's no displacement, but at antinodes, there is maximum displacement. And of course, you can increase this more and more, and hopefully that, of course, that'll be enough for understanding this one here, because there is also another question that we need this for. Okay, so now going to this equation. What if the question is asking you to find the wavelength of any standing wave here? There is one easy method to do that, Basha, and you have to use this equation right there. So for example, using this diagram right here that I drew here, let's say the length of this wave, the length of, or not the length of the wave, the length of the string here, it is 5 centimeter. Actually, that's too short. Let's say the length of the string is 20 centimeter, Basha. Right, 20 centimeter. What is the wavelength on this, or of this standing wave here? We have an equation. The equation says the wavelength for any standing wave here, you can say, let's say the wavelength of any standing wave, it can be found, Basha, by using this equation, which is equal to 2 times the length of the string divided by what? Divided by the number of antinodes here. All right, even though at chapter 4, we have the same equation, and there we'll switch this letter A with N. That'll be the number of harmonics, but it's a bit early for this. So just keep in mind, this A stands for what? Stands for antinodes. Stands for what? Antinodes. All right? Okay, so can we find the wavelength here? The wavelength for the first wave, we can say. We said it is equal to 2 times the length divided by how many antinodes do we have in here? There is only one antinode, right? So we'll say 2 times the length divided by antinode, which is just going to be 1. So 2 times 20 divided by 1, that is going to be 40 centimeter. Or you can say 0.4 meter. That'll be the wavelength of the first wave here. Basha, can I find the wavelength of the second wave? Absolutely, yes. Okay, didn't we say the length of the string is equal to the wavelength here? Basha, we can say, let's say the wavelength of the second, that is equal to 2 times L, which is 20. But how many antinodes do we have now? There are 2 antinodes, Basha Baba. So 2, or divide by 2, this to cancel out, so it is just 20 centimeter or 0.2 meter here, whichever that is given here. What about here? Okay, so the length of each one of these strings is 20, don't forget. So the wavelength of the first wave, third wave, that is equal to 2 times the length, which is 20, divided by how many antinodes do you have? You have 3 antinodes, so just divide by 3. So that is going to be 40, divide by 3, whatever the answer is, you just find it out. That is going to be this much centimeter. And then, of course, you can convert that to meter as well. This is how you can find the wavelength of any wave that is given by using this equation. Basha, what if they did not show you the diagram, which most of the time they do if they ever ask for, but let's just say they did not show you the diagram. So we have a wave. That wave has 10 nodes, Basha, keep or write it down. It has 10 nodes, all right? The length of the string is, it is 20 meter, Basha. What is the wavelength of each wave that is on that wave, right? So let me tell you what exactly I mean, or the wave that we have. We have a wave, Basha, and this wave, right, the question would not show you the diagram. It just tells you that we have 10 nodes, Basha. So the number of node is 10, Basha. All right, so find the wavelength on that string if the length, right, of the string, all right, is, we said 20 meter, Basha. We have a string. The length of the string is 20 meter. Basha, 20 meter. On this string, there is a standing wave. That standing wave has 10 nodes. Basha. So what is the wavelength of this standing wave here? So easily we could do that. Remember the equation to use. Gutman, 2 times the length divided by the number of antinode. Basha, 2 times the length. It is 20 meter divided by the number of antinodes. But do we have the number of antinodes? No. But if you remember, we said number of antinode, it is always 1 less than the number of what? Of nodes here. If you have 10 nodes, Basha, minus 1, that is going to be 9 antinodes. So now we'll just divide by 9. It is going to be 40, divide by 9. So whatever the length is, the wavelength equal to that much meter there. Okay, you can calculate this one. As a matter of fact, let's just calculate that. So 2 times 20, and then divided by 9, the answer is going to be 4.4. So the length of each wave, it is going to be 4.4 meter. That's how easy it is, Of course, be open to different ideas so that you make sure that you're not going to lose any marks at all. Right? So that is what we have. So the number of antinodes would be, if you ever need to do that, that would be nodes minus 1. But if you ever want to find the number of nodes, would be the number of antinodes plus 1. Now the last thing that is left in here is this node right here. The last thing that I need to tell you is this one here. Watch this. We have a standing wave, right? And it would be best if you color one of these so that you can see the difference better. So let's say this is one of the waves that we have. So now this is we can say, standing wave that we have. The other one is going to be the same wave, but after some time is going to switch sides here. Basha? So the first part that we have says the separation of adjacent nodes is half a wavelength. We've never mentioned this one here, yeah? So how do we measure, let's say here we have a standing wave, Basha? So how do we measure the wavelength and all that on a standing wave here? Okay, so now we said we have nodes, Basha, we have antinodes, and then there is another node, should be a little bit lower, but doesn't matter. This is, these are antinodes, and these are, of course, nodes and nodes and nodes. Watch this here. So if I ever ask you what is the wavelength here, do not ever say the distance between one antinode to another, that is one full wavelength. No. Why? Because these are, remember, you can see these are different. These are the same wave here, but of course at different times here. Okay? So if you ever want to know that, starting from a point, if we, for example, look at this orange wave here, or the light red whatever right here, starting from this point all the way here, that'd be one full wavelength, Basha. But how much is this? Starting from this, right, all the way to this, that is one full wavelength, yes or no? This much. Yeah, Basha. Now, so what about this one here? Isn't that half of, it's right between these two antinodes in here? Because this is the wavelength that we have. So at this point, we can say just let us cut this short actually. So the distance between two antinodes, that is going to be half a wavelength. Don't forget. So once again, the distance between one antinode to another, right? That is half a wavelength. Half a wavelength. What about, let's say, the distance between two nodes in here? But remember, these nodes must be adjacent. What do we mean by adjacent? That means one after another. Basha? Without any other nodes being in between. So the distance between two antinodes, right, that is going to be half of a wavelength. The distance between two nodes adjacent, these are, again, half a wavelength here. What about the distance? Watch this. The distance between one antinode to the adjacent node in here. All right, let me show you something clearer maybe. All right, so this wave right here. So is this supposed to be clear? Okay. So here we have a standing wave. Let's use a different color too. That is a standing wave, Basha. So quite mindly, one antinode, or the distance between one antinode to another, that is half a wavelength, Basha. And then from one node to another, that is also half a wavelength. So watch this. This distance here, it is half a wavelength, Basha. What about the distance between one antinode to the adjacent node, this much right here? Well, Basha, if this is from one antinode to another is half a wavelength, what about this one here, which is right in between? Can I say it is a quarter of a wavelength? Yes, and that is what you're supposed to say. Perhaps if you draw them a little bit further away, it might be even easier to notice this. Okay, this one was too close to one another. So this distance here from one antinode to another, that is half of a wavelength. Basha, what about this antinode to this node in here? Isn't that half of this? Basha, what is half of half? That is going to be 1/4. So it is 1/4 of a wavelength. Of course, expect questions like this in Wuzari because these are very important, Basha. So Kata, the separation of adjacent nodes is half. The separation of adjacent antinodes is also half. And then jump to point number 4. The separation between adjacent nodes and antinodes, it is one wavelength divided by 4. And then we also mentioned that at maximum, where the maximum amplitude is 2, which is twice that of a single wavelength. That is, we've mentioned, if you remember, we said Gutman at antinodes, this is the result of constructive one, yeah? So at this point we have two pulses. If each one of them has one amplitude, then the resultant is going to be 2 amplitude, which is twice the amplitude of each one of these waves right here. Now, what about point number 3, right? I don't think they'll ask you something like this, but this separation between two antinodes where the phase difference between the two is 0, it is one full wavelength. What do you mean by this? Now, this is 1 point, or if you take 1 point on a wave in here, what is the same exact point on the next wave here? When we say the next wave, not this wave here, you'll have to go on this wave here. So let's use the same color so it doesn't mix up. So the same point on the next wave, that is this antinode here. So the distance between this antinode to this one, it is going to be one full wavelength. All right. I think that was too much. Yeah, it's the end of this section, huh? Let's just see how far we can go. All right, so we're going to answer these questions. All right, the first question to begin with, what does it say? It says a wave of amplitude, Basha, of amplitude 0.3 meter interfere with the second wave of amplitude 0.2 meter. What is the largest resultant displacement that may occur? All right, watch this. So here, right, so whenever it says what is the largest, write this as a study tip, all right, or as a note for yourself. Okay, whenever it says what is the largest amplitude that we can get, that means this is, in order to get the largest, you must combine the two waves. If you combine them, that is going to be constructive interference, Basha. So we have a wave amplitude. Let's say here we have just a pulse, Basha. Length it is 0.3 or 30, you could say, 30. And then there is another amplitude here. This amplitude, it is 0.20. These are both in meter and meter. Okay, so what is the largest resultant displacement that it may ever occur? The largest can occur if these two are both combined, right? If these are both on the same side. So you just add them here. 0.3 and 0.2, it is going to be 0.5 meter, all right? So that is going to be the largest that we can ever get. Now, remember, the second one is something very important. Questions like this have been in Wizari several times. So you have to know your keywords, Babadira. But let's see. A string is rigidly attached at a post at one end. If you're not careful, you might just read this one. And of course, this keyword might slip right away in your hands here. So several pulses of the amplitude of 0.15 meter sent down the string and are reflected at the post and travel back down the string without any loss of the amplitude. That is also another keyword. Yani whatever the amplitude is never going to be lost, okay? The same amplitude will get back. What is the amplitude? At a point on the string where the maximum displacement points of these two pulses cross. So once again, if you're not careful, you don't know whether this is constructive or destructive, but there's always a key hidden right here. It says a string is rigidly attached. I need you to underline this for me. When a string is rigidly attached, we said if it is rigidly or fixed end or is attached, it's not rigidly attached, that means fixed end. Yan Bablin, fixed boundary. Fixed boundary. Ebasha, if we have a fixed boundary, we're sending a pulse, right? Then what happened to the reflected pulse? It is reflected and inverted, yes or no? So see, so now one of them is up, the other one is down. And it is the same amplitude because the question says without any loss of the amplitude, Basha. So that is going to be 0.15 up and then 0.15 down. So now the question is, what happened when these two waves meet? Of course, one up, one down, so they're going to cancel one another out completely, or you can say this results in a complete destructive interference in here. All right, so once again, what will be the amplitude of the resultant? The resultant is going to be 0 because we have one is up, which is positive, the other one is down, negative, so 0. That is going to be the resultant amplitude. The second part of the question says, what type of interference is this? It is going to be complete destructive interference. Basha, the question, for example, said a string is attached to a ring bubbling, and attached to a free end boundary, okay? The whole thing would have changed, of course. In that case, you would have just added, just like this one right here, and the type of the interference would have been constructive interference. But here, we don't have that. Okay, perhaps that would be for the second one here. See, it says what would happen, or what would be the amplitude of the pulse in item 2 in question 2 if the same pulses were sent down a string whose end is free. Again, this is a keyword. If the end is free, the pulse is sent, it is reflected but not inverted. Now these two pulses are both on the same side, so once they meet, we'll combine them. So again, combining the resultanta كده 0.15 and 0.15, that is going to be 0.3 or 30, and then that'll be a constructive interference. All right, that'll be the end of this session. Inshallah, next time we're going to continue with the other questions. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.